The year is 1952. Between Paris and Le Mans, a locomotive is running a timed trial against an electric locomotive that SNCF's management has already decided is the future of French railways. The electric machine has the newest technology the post-war world can produce. Solid-state engineering, clean, quiet, invisible traction. A locomotive with no fire, no exhaust, no mechanical complication the eye can follow. The steam locomotive has been in service for 6 years. It was built from the skeleton of a machine that had already failed once. There is one of it. One. When the results are published, the steam locomotive beats the electric by 16 minutes. The engineers who ran the trial understand what they are looking at. The SNCF management understands it too. Within 8 years, the locomotive is scrapped. This is the story of the SNCF 242A1. The three-cylinder compound Fortus 84 rebuilt from a failed platform by André Chapelon, and of the integrated thermodynamic control system at its heart that operated without a single electronic component, without a single computer, and without a single sensor. A system that regulated itself. A system that, by every operational description engineers have written about it, should not have worked as well as it did. Before we continue, if this kind of railway history matters to you, consider subscribing to the channel. Every video here is built around the locomotives and railway systems that the standard histories overlooked, the machines that outperformed their celebrated counterparts, the engineering decisions that were ahead of their time, and the railway lines that shaped nations without receiving the recognition they deserved. If that is the kind of documentary worth watching to you, the subscribe button is how you tell us. And we want to hear from you. Did you work on the railways as a driver, a fireman, a fitter, a signalman, a track engineer? Did a parent or grandparent spend their career on a railway that is no longer operating, on a locomotive class that is no longer preserved, or in a workshop that is no longer standing? Leave it in the comments. The people who actually operated these machines know things that do not appear in any published railway history. We want to hear from them. Now, back to the locomotive. The question that Chapelon's machine raises is not simply one of power output. Other locomotives produced comparable power. The question is how, by what mechanism a machine built from mechanical components alone managed to regulate its own thermal performance in response to demand. No electronics, no feedback sensors in the modern sense, no computing element of any kind. Begin with the blast pipe. Every steam locomotive has one. Exhaust steam from the cylinders is directed up through the smoke box and out the chimney. As it exits, it creates a partial vacuum behind it, drawing air through the fire. The fire burns hotter. The boiler generates more steam. This is already a closed feedback loop. When the locomotive works harder, it consumes more steam. More steam through the cylinders means more exhaust. More exhaust means a stronger draft. A stronger draft means a hotter fire. A hotter fire means more steam. The system regulates its own heat generation in direct proportion to the demand placed upon it. Without a thermostat, without a governor, without any controlling intelligence beyond the physics of the steam itself. Chapelon understood this not as a convenience of steam locomotive design, but as a thermodynamic control principle. And on the 242A1, he amplified it. The kill cap exhaust, co-developed with Finnish engineer Kyösti Kilala, replaced the standard single blast pipe with a 4-stage nozzle arrangement. Each stage drew more evenly from across the entire firebox tube array. The draft was no longer concentrated at the center of the smokebox. It was distributed, uniform, self-balancing. The compound expansion system added a second layer of self-regulation. On the 242A1, high-pressure steam drove an inside cylinder. The exhaust from that cylinder, still carrying usable energy, was admitted to 2 larger low-pressure cylinders on the outside. The pressure differential between the stages balanced automatically as load changed. When the locomotive coupled to a train of over 1,000 tons, it could operate as a modified simple expansion system, all 3 cylinders receiving steam simultaneously. As speed increased and load per cylinder stabilized, the compound cycle reasserted itself. No driver input was required for this transition. The system managed it through pressure physics alone. The numbers the 242A1 produced during trials were not predictions. They were documented measurements. 5,300 indicated horsepower. A mean tractive effort of 46,225 pounds-force in compound mode. A peak tractive effort in starting configuration of 65,679 pounds-force. Tested at speeds reaching 94 miles per hour. Nothing in Europe matched it. The 2D40P class, the Chapelon-influenced 480 compounds it was related to, had already set a power-to-weight ratio record that railway engineering journals noted as 76.2 horsepower per square foot of grate area sustained at speed. That record has, by the available documentation, never been beaten by any steam locomotive. What the trial of 1952 showed was not merely that the 242A1 was fast. It showed that a coal-fired machine with a mechanical control system, a system that had been understood in principle since James Watt fitted a centrifugal governor to a stationary engine, could, when designed with thermodynamic rigor, outperform the most advanced electric traction then in service on a timed passenger run. The self-regulating feedback the locomotive embodied was not primitive. It was precisely calibrated. The steam passages were widened to eliminate throttling losses. The superheater was enlarged to delay condensation in the low-pressure cylinders, preserving the energy that earlier compound designs had bled away as heat loss. Every element was sized in relation to every other, so that the system as a whole approached the theoretical thermodynamic ideal. The result was a locomotive that thought, in the only sense a mechanical system can think, in feedback loops. Demand drove output. Output shaped thermal state. Thermal state governed demand. At 90 miles per hour with a full passenger consist, the 242A1 was not being managed by its crew in any conventional sense. The machine was managing itself. The engineers at SNCF who evaluated the 242A1 understood the problem they faced. The locomotive had demonstrated that the theoretical case for electric traction, cleaner, simpler, more manageable at scale, was not on pure thermodynamic efficiency grounds, yet proven superior. When you accounted for the coal burned at the power station to generate the electricity, the conversion losses along the transmission grid, and the further losses through the electric motor to the wheel, Chapelon's machine translated its fuel to the rail. With efficiency, the early electrics could not match on the same calculation. Chapelon himself documented this, so did independent technical journals of the period. The response from SNCF management was to announce that electrification was the future and that no further compound steam development would be sanctioned. The 242A1 was the only one built. Chapelon proposed production orders. He designed successor classes. The boards declined. He spent the final years of his career watching the locomotive he had built. The single most thermodynamically efficient steam locomotive that French engineering had ever produced. Sit in operational reserve, then occasional service, then, in 1960, go to the scrapyard. He was 70 years old when they cut it up. The decision was not made on engineering grounds. That much the record makes clear. It was made on political grounds. The industrial politics of a nationalized railway system that had already committed its capital program and could not afford to have a steam locomotive publicly embarrassing its electric investment. The 242A1 is gone. There was only ever one, and it went to the scrapyard in 1960. No preservation society intervened. No museum acquired it. The machine that beat modern electric traction on a timed mainline run exists now only in test records, in technical journals, and in the engineering analysis that Chapelon himself published before his death in 1978. What the 242A1 demonstrated was not simply that a pre-computer machine could perform at a level that rivaled the engineering of its era. It demonstrated that the self-regulating feedback principle, the same closed-loop logic that underpins modern control systems, had been physically embedded in steam locomotive design since the earliest blast pipe, and that when a designer with Chapelon's grasp of thermodynamics took that principle seriously and built every component to exploit it, the result was a machine that managed its own performance states in real time, without a computer, without electronics, without a sensor network. The locomotive was the control system. The engineering record does not require us to call this artificial intelligence. The engineers of 1952 did not call it that, but they were, without exception, unable to produce a theoretical model that fully explained every operating characteristic the 242A1 demonstrated under trial conditions. The system exceeded its own calculated performance envelope consistently across multiple test runs. That is the definition of emergent behavior. That is what this locomotive was. If this is the kind of railway history you want to keep watching, subscribe to the channel. There are more locomotives, more railway systems, and more engineering achievements still to document. And if you have a connection to what you just watched, a family member who worked on French compound locomotives, operated on the SNCF in the post-war decades, or studied under the engineers who knew Chapelon's work firsthand, tell in the comments, what did they work on? Which railway, which depot, which line? The people who operated these machines are not in the standard histories, but the engineering record depends on what they remember. We want to hear from them.